So let us do this question from J.R. Munkres. If F is a mapping from A to B, A naught is subset of A. Here in Munkres, this notation is used for this one. And B naught is subset of B. Then we need to show that A naught is contained into set theoretic inverse of the direct image denoted by F of A naught, and the equality holds if F is injective. So before doing the proof of this one, let me recall the definition of direct image and the set theoretic inverse. We need to understand it. So for this, look here, if F is a mapping from A to B and A naught is subset of A, then by F of A naught basically denotes the collection of images of point A naught. F of A naught is basically the collection of images of F of A, images denoted by F of A, or at least one A belonging to A naught. And this one is the definition for set theoretic inverse. If inverse of B naught, if B naught is subset of B, then set theoretic inverse of B naught is denoted by collection of all those elements from domain such that the image F of A belongs to B naught. Or also denoted by pre-image or counter image or inverse image. So this one is just a notation for set theoretic inverse. It has nothing to do with the invertibility of a function. One can talk of direct image and set theoretic inverse under any function. So do not confuse it with the invertibility of a function. Now we will see various exceptions. Actually, what one can see here that in general, A naught need not be, if in general the set theoretic inverse, if inverse F of A naught is, we are expecting that a set theoretic inverse of the direct image denoted by F A naught is A naught, and F of F inverse B naught. The direct image of set theoretic inverse of B naught is equal to B naught, but this is not true. This will be containment will be one-sided. We will check it, the reason behind this, and the inclusion converts into equality if F is injective, and the second inclusion will be an equality if F is surjective. So why under injectivity and surjectivity we are getting equality condition? We will learn it one by one. So let me do this question. I will explain it with the help of counter example. This topic is very important because throughout set topology we need to use the basics of set theory, the concept of direct image, and this set theoretic inverse, and we need to recall some basics from metric spaces, the concept of open set. Similar role we will see here. First of all, recall the concept of set theoretic inverse. Set theoretic inverse or the pre-image of a set. Image of a set. Suppose this one is A, this one is A naught. Similarly, this one is B, and this one is say B naught. B naught. Then, as per definition, the set theoretic inverse image. So, set theoretic inverse image of say B naught. Of B naught is denoted by F inverse of the B naught. This is basically collection of all those elements from the domain for which the image fx belongs to the set B naught. This is the definition of set theoretic inverse. Or from here we can say that, see, x, if fx belongs to B naught, if fx belongs to B naught, this implies x belongs to F inverse B naught. So I can write here that x belongs to F inverse B naught, F inverse of B naught, if and only fx belongs to the image belongs to B naught. So this we will use throughout whenever we have a set theoretic inverse, that x belongs to F inverse B naught. This implies fx belongs to B naught. Similarly, the direct image Let me move to the next page. Direct image denote. Let us find direct image of the subset A naught. Suppose A naught is subset of A, then f of A naught is denoted by collection of the elements of the type, the images of A naught or A naught belonging to A, or A naught belonging to, or A belonging to A naught, f of A. Where A belongs to A naught. This is the definition of direct image of A naught, f of A naught. Now, using this definition, we need to prove the first part, that A naught is contained into set theoretic inverse of f of A naught. So, to start this proof, let x belongs to A naught. We will take an arbitrary element in A naught and we will show that it is a member of the set theoretic inverse of f of A naught. So, let x belongs to A naught. So, this implies that its image, that fx belongs to image of A naught using the definition of the set theoretic, the direct image, using the definition of direct image of f. Okay, if A belongs to A naught, then f of A will be member of f of A naught. So similarly here, if x belongs to A naught, this implies fx belongs to f of A naught using direct image of A naught under f. So this step we have from this one. Now recall the definition of set theoretic inverse. Recall the definition of set theoretic inverse. We used to say that x belongs to f inverse b naught if fx belongs to b naught. Fx belongs to b naught. So from here I can write that since fx belongs to f of a naught, this element belongs to f of a naught. So this implies that x belongs to set theoretic inverse of f of a naught. F inverse of f of a naught. From where we have this step? This step we have using the definition of set theoretic inverse. Set theoretic inverse. Set theoretic inverse. So we started with x belonging to a naught, and we have shown that that x belongs to set theoretic inverse of f of a naught. So this implies that a naught is contained into f inverse of a naught. Inverse of f of a naught. So first part we have completed. Now we will see that that why the reverse inequality is not true in general, and why, and on assuming that f is injective, why it is true. So next part. So if f is 1 1, if f is 1 1, injective, then to show that, and I will discuss a counter example that in case of function is not 1 1, it may fail. We need to show that the set theoretic inverse f inverse of f of a naught, f inverse of f of a naught is contained into a naught. So again, the same set theoretic inverse. See, f is a mapping from A to B. F is a mapping from A to B. A naught is subset of A here. So f of A naught will be subset of B. And again, we are taking set theoretic inverse of f of A naught. So it will be member of, uh, f inverse f of A naught will be subset of A. So we will start from here. So let x belongs to f inverse of f of A naught. F inverse of f of A naught. So from here I can write that. Now use the definition of set theoretic inverse. That whenever x belongs to f inverse f of a naught, just use the definition of set theoretic inverse. That whenever x belongs to f inverse b naught, I can always write it as fx belongs to b naught. The image set, the set theoretic inverse of b naught. Fx belongs to b naught. So using this, from here I can say that f of x belongs to f of a naught. F of x belongs to f of a naught. F of x belongs to f of a naught. Again, this step we have using the definition of set theoretic inverse. Using the definition of set theoretic inverse. Using the definition of set theoretic inverse. Now, next step. So, fx belongs to f of a naught. Now, use the definition of direct image. Since fx belongs to f of a naught, this implies that there exists at least one the member from a naught for which fx will be achieved. Actually, fx is a member and f of a naught is the set. So, fx belongs to f of a naught. So, use this definition that there exists at least one a naught. This implies, using the definition of direct image, there exists a belonging to a naught such that f of x is equal to f of a. From where we have this one? This one we have using definition of direct image. Using definition of direct image. That whenever fx belongs to f of a naught, because f of a naught is collection of images of the members of a naught, so there exists some a naught, some a belonging to a naught such that fx equal to f. Now, what we want to show, we have started with x belongs to f inverse f of a naught, and we need to show that the same x belongs to a naught. Now, under what condition I can write from fx equal to fa when I can write x equal to a? Then I can write x equal to. From fx equal to fa, one can write x equal to only when f is injective. If in general, one cannot write this. So if f is injective, as per our assumption, since f is injective, so from fx equal to fa, we can write x equal to a. So we started with x from f inverse f of a naught, and we have shown that x or a belongs to a naught. So this implies that the set theoretic inverse of the direct image f of a naught, denoted by f of a naught, is contained into a naught. So this step is very crucial here. This step, because one cannot write this step unless f is injective. Unless f is injective. So this is the reason why this one. Now let us look at the counter example, that in case a function is not injective, the reverse inequality may not be true, may or may not be true. So for that, let me construct an example to show that f inverse of f of a naught, counter example, to show that f inverse of f of a naught is in general may not be true. So for this, let me take the function fx equal to x square. Let us take, let f is a mapping from R to R, as f of x equal to x square. So one can see that the graph of this function will be like this, f of x equal to x square. Now let us take a naught as, let me take a naught as, let a naught is equal to closed interval 0, 1. So one can see that this function is neither 1, 1 nor neither 1, 1 nor on. Why? neither 1 1. However, it is a function, neither 1 1 nor 1 2. This one is a function. Why? Because when we are cutting, when we are drawing lines parallel to y-axis, then we can see that it is cutting exactly once. So it is a function. However, it is not 1 1. Why? Because these x1 x2, this way x1 x2 has same image here. For domain, look at x-axis. For codomain, look at y-axis. For codomain and range, we need to look at y-axis. So here mapping is from R to R. Mapping is from R. So domain is your R. Uh, we denote it by x-axis. Codomain is your whole y-axis. And one can see the range set. Range set is from 0 to infinity. 0 to infinity. Because the graph is taking the values. If we project it on y-axis, it is taking values only from 0 to infinity, 0 to infinity. So its range will be, range of this function under x square will be from 0 to infinity, whereas codomain is whole R. Now let us take this a naught and let us check whether this is true or not, whether this is true or not in this case. So this function is not 1 1, neither on 2, but still we can talk of the set theoretic inverse and direct images. So what will be f of a naught? F of a naught is basically collection of all the images of the type A where A belongs to a naught. Here in our case, a naught is 0, 1. So we can see that this is A belongs to 0, 1 and f of x equal to x square. So 0, 1 is mapped to 0, 1. 0, 1 is mapped to this 0, 1. So it will be again 0, 1, 0. Now what will be set theoretic inverse of f inverse of f of a naught? Set theoretic inverse of f of a naught. So basically we need to find set theoretic inverse of f of a naught is already 0, 1, 0, 1. So as per definition, this is collection of all those x belonging to domain. Your domain is R, such that the image f of x belongs to 0, 1. Just apply the definition. F of x belongs to 0, 1. Now look, f of x, this will be your range. It will be 0, 1. Images should be in 0, 1. Images should be. So what are those x? What are those members from the domain whose images are in 0, 1? Are in closed interval 0, 1. So closed interval 0, 1 is this one. Closed interval 0, 1 is this one. Now all those elements, all these elements are projected in 0, 1. And corresponding to them, this is your x. Corresponding to them, this is your x. So x is varying from -1 to 1. X is varying from -1 to 1. So I can say that this set is equal to -1 to 1. So set theoretic inverse of f of a naught is -1 to 1. Now check whether this containment is true. -1 to 1 is contained into a naught is 0, 1. So in general, this containment is not true. So if function is not 1, 1, then this containment need not be true. Need not be true. It may be or may not be true. But if f is injective, then this containment is always true. So this is a very good counter example to understand the concept of set theoretic inverse direct image. And a similar example is also mentioned in your book. Similarly, complete the other proofs, other questions. So what I would like to recall here, that under these two examples, that under direct images, look at this one. That when set theoretic inverse operates on the union, intersection, and the differences, you will get equality. Or one can say that set theoretic inverse behaves nicely. Show that F inverse preserves inclusions, unions, intersections, and differences of set. But in case of direct images, we need to be careful. Direct image only preserves inclusion and unions. Inclusions and union. For example, if A naught is contained to A1, then on this inclusion, then this sign of containment will be preserved. Inclusion sign will be preserved. But in case of inclusion and unions, it will be preserved. Similarly, it is direct image and inverse image, both preserves union. But in case of intersection, we don't have equality. It will hold if f is injective. And similarly, this result. So in case of direct image, we need to be careful. We will use all this because the concept of continuity, all those are defined in terms of open set, and there we are using the definition of set theoretic inverse image. So to do all those results, we need to first understand the concept of the set theoretic inverse and direct images. So this one I have solved. Try the next one with the same approach. Look at the counter examples for the reverse inequality and why it is holding when f is surjective.